now we can get going. Here's our outline for today. I'm actually going to talk about a few housekeeping details that I talked with some students about yesterday in office hours. Don't forget, office hours are a great time to study with me. If you feel like, Dr. B, I'm just not getting this one equation about potential energy or anything, Wednesdays from 11 to 1, my official office hours are really good. And sometimes you just need another person to talk to. Now, SI will help you out in the same way. All right? You go to SI and Maria can help you get squared away on different concepts. And the other nice thing about going to SI is you can make a friend. And maybe a friend that will be a good study partner with you. And the reason I emphasize that is because the main study suggestion I have for everybody is, in addition to just coming to class every day and doing your homework every day, is find somebody to study with, either me in office hours or a friend or SI. Anything like that is going to help you, because sometimes, like I was talking to a student yesterday in office hours, and he got stumped on something because he studies by himself. And he said, Dr. B, I kept getting it wrong. And on the some calculation that we were talking about, and I said, well, let's take a look at it. And we got it squared away. But that's what I told him. One nice thing is if you can make friends in class, or if you have a roommate, or somebody in one of the, even in the other section, that'd be good too. It's always good to do that. Second thing I want to mention is that this is the halfway point of the semester. This is lecture 14 today. And we usually get about 28, although I think this semester we're getting 29 lectures, if I'm not mistaken. But yeah, we're right about the halfway point. Another thing I want to mention, now you guys are mostly in front of the railing the way you're supposed to be, but some of you are not. And we had a student in the 10:30 lecture that usually sits way in the back, in the bad boy row. And the bad boy, I call it the bad boy row because, like on school buses, the bad boys always sit in the back row. And Connor, you're laughing because you're not a bad. You can't tell me that you were one of the bad boys. Okay. Anyway, so he's all the way back in the very back row, and we tested it out after lecture. We dismissed a few minutes early, so I did a test run with his clicker because he said, "Dr. B, I have a really low number on my answers. My hundredths point, tenths and hundredths fraction, part of my roundup figure is really low." And I said, well, let's just do a test run. So we did it, we did a little mini session with the iClicker. And first he did it, he and another few guys, they were three guys right up in the front row, 3 clicks. And then I said, all right, go back to the back row. And we got 2 clicks from the guys in the front and none from the back. And then he came, okay, a young man with the blue shirt and the baseball hat. Raise your hand. What's your name? Reggie. Back about where Reggie was, he started, right about Reggie's row, I started picking up his clicks. Now, it may be that he has a faulty clicker. He rented it. So he rented it used. All right. And I said, look, go get some Energizers or Duracells in there, because sometimes it's those El Cheapo batteries that it comes with. And I suggest that for everybody here, that if you feel like your roundup figure that I posted last week is a little bit low, if you're here every lecture but you don't have 23 something 0.23 for your clicking roundup, maybe move forward a little bit up to about where Reggie's at, maybe, or closer. And definitely there's space. So, all right. So questions about that? Get your clicker out. We're going to click in a few seconds. Okay, let's keep going. I want you to go into your grades page. I'm going to show you, for those of you that asked to have the PDF of your Scantron results in homework 00, which a bunch of you did, the way that you get it is you go into your grades page. Now down here on the row that's set up for exam 1 Scantron, you'll see a little icon. You know, it looks like a discussion icon, but it's actually a message icon. All right, here's a close-up of it. All right, and what you do is you click on that, and that'll bloop open a little sub window that looks like this. All right, and in that sub window will be at least one message that basically says, you know, here is your exam 1 Scantron results PDF. So let me focus in on this. There's the actual file, and there it is. So you'll see, you click on that little icon, it'll pop open this sub window, and then you'll download that PDF. Everybody that asked for one has got one. All right. And when you do, when you download it, it'll look, you know, like this. I did show you this last time. Here's this is a real printout. Yours will look like this in PDF. And you'll see, you know, which questions you have right and all that kind of stuff, what you answered incorrectly, what your answer was, what the answer key was. And so with that Scantron results PDF and the blurb files, which are also set up, here's the blurb file page, and you guys are in the left-hand column. You can make a nice little mini study guide for yourself, because your Scantron PDF will tell you which ones you got wrong. And then the blurb file will tell you all those ones that you got wrong, what were they basically about, okay? So they're not verbatim. If you want verbatim, if you want to look at the actual exam, that is fine. But you have to come in for office hours for that, all right? And I do it every semester, and it's a good, you know, you can just read it. Oh, yeah, I remember now. You know, this number 17 that got me tripped up. And sometimes I actually go and dig out your actual exam paper. And I might actually do that for this class because it's kind of a small class. But I have an unused exam form that is that you'll be able to use. And if I feel like there's time, I might dig yours out and stuff. So, all right, now questions about the Scantron results PDF. Question? Go ahead.
How long before you can go to your office hours?
Wednesdays. Every Wednesday at 11 to 1. Okay? So the question was how long before I can go to my office hours. And unless you go over to my office, my regular office, which is room 156 in the physics building, and you catch me, which I'm over there, various times, but it's no guarantee. I might be out and about somewhere working on something, so. But I mean, if you can catch me outside of my regular office hours, 11 to 1 on Wednesdays, then yeah, you can, I'll dig it out for you, stuff like that. Another question. Okay, and just to reinforce, I have already done this with a student that came in during office hours, and that student definitely got their PDF. It looked good. So it all works. So if you ask for it in Homework 00, you've got it. Now the 1030 section, I've got about half of those guys done. So that's good. Now, another thing I want to bring up to you, I did a new talking PDF about freefall energy levels, and I put it in web courses yesterday afternoon, yesterday afternoon, and I put it in announcements and stuff, so hopefully you got to look at it and use it. And basically, here's what it looks like. It's, just a table, and I work through a couple rows of the table, the top row, the bottom row, and then I think I do 3 meters. This is a table from 12 meters on down, and for a box of Doritos, 1.72 kilograms. I mean, you could do anything you want, but so I calculated gravitational potential energy, kinetic energy, total mechanical energy, E. And then I actually went past that and I calculated V squared and then V, the downward speed. And you can do that as well. Now, I want everybody in here to download that and listen to it, okay? Because exam 2 is coming. And if you have studied and thoroughly understood this freefall table, and I didn't, as you can see, I didn't fill in all the rows. I left some rows for you to work on. And if you come to office hours, we'll work on them together and re-verify your results, okay? And here's something that I want to emphasize. I emphasized in the talking PDF, and I'll emphasize it again now. There is a pattern. If you make, as I did, equal increments of delta y, then you'll find equal increments of GPE and kinetic energy. You'll also see equal increments of V squared. Now, why is that? The reason that you'll see it, and that's why the V squared column is handy, because you'll see a pattern in the V squared column. Now, the E column, the total mechanical energy, there's a pattern there, ditto marks all the way down. Right? You can see a bunch of ditto marks there. So that's a pattern, I guess. But the V squared, the kinetic energy, and the GPE columns, yeah, there's equal increments all the way down. And it's important in the V squared column because it's not V. The V column, when you separate it meter by meter, the downward speeds are not equally incrementing. But V squared is. And you'll see it when you do, and you'll see it when you look at the talkie PDF. And then when you fill in the rest of the rows, you'll see it in meter by meter. All right, if you do it carefully and you do it correctly. So now I have a iClicker question for you. And this is going to be a survey type question. So just answer. Here's the question. Have you used it as of 9 a.m. today? Yes or no? And either answer is going to be graded correct. So just tell me what you've got. And boy, it's pretty pathetic here. No? Okay, well, I'm getting a few more. Just tell me what's true. I shouldn't say it's pathetic, but it's fewer than I was hoping for. Okay, 10 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Okay, so 87% of you did not use it yet, but I want 100% of you to use it between now and exam 2. All right, so Now, we're going to try some more freefall energy calculations, and this is by way of reinforcement. But these freefall energy calculations are going to be on the moon. Now, on the moon, the mass of the moon is 0.0123 of Earth's mass. And its radius is about 0.2725. So it doesn't have a lot of mass, and it's about 27% of the radius and diameter. So its G value is a little bit smaller. Here it is. Negative 1.62 meters per second squared. And I mentioned that a few times ago. We mentioned that if you look at the movies of the Apollo astronauts, they can leap like deer up there on the surface of the moon. All right. Now, we're going to use this fact, G equals negative 1.62 meters per second squared. And actually, we're just going to use positive 1.62. We're just going to do some stuff with it first. And what we're going to do with this, fairly smallish gravitational surface gravity, acceleration of gravity at the surface of the moon, we're going to calculate the weight force of a hammer, okay? And those guys, one of the Apollo missions they took a hammer and a feather and they dropped them together at the surface of the moon, and they fell, because there's no air up there. To make, a feather in Earth's atmosphere would, kind of skip and float through the air. But up there on the moon, they fell at the same rate. So go ahead and write down the mass of the hammer. Hit your refresh key, and let's do a multiple choice question. Here's your multiple choice question. What's the weight force of the hammer? And here I do have negative signs. So the weight force of the hammer on the moon. Which is heavier, a ton of bricks or a ton of feathers? Ton of bricks and a ton of feathers. Did you ever do that, like in 5th grade? Did you ever tell that joke? Yeah, it's good. All right, so we have a weight force of a hammer. So the weight force on the moon is different, but of course the mass is the same. Same number of protons and neutrons and stuff. Okay, you guys are doing good. 30 seconds. Whew. 15 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay, good. 94. 94 students. Sorry, my leg cramps. Good. 76% of you got that one right. Go ahead and jot it down. And if you got tripped up, a few of you got tripped up on it. Actually, 81% of you got it right. Here's the calculation. Go ahead and jot that down. It's just W equals mg, but G is the G of the moon. All right? And, see what I missed in my equation there? W equals, see anything missing? No. Forgot my minus sign. Dr. B. I'll have to correct it for the... actually, I think I can correct it for the YouTube. All right, so there it is, just W equals mg. Now, we're going to use that to calculate potential energy on the moon and stuff like that. And that's where we're heading. All right? And let's get set for that. Now, once you set the baseline elevation for calculating potential energy, y equals 0, then you can, it simplifies things, among other things. Your GPE, the few of you that did look at the table, the talking PDF, it actually simplifies. GPE becomes minus mgy. In general, it's minus mg delta y. But if, depending on where, so if you're on the surface of the moon and there's nothing, nobody's tunneling down underneath, you may as well just set y equals 0 at the surface of the moon. Like in this one, but now versus this classroom, I could set y equals 0 here to be the height of the stage. And then the skateboarders down here in the very front, they'd be at y equals negative like 1 meter or so. All right? And then my hand up here would be at, like y equals positive 2 meters. All right? So there it's a little trickier. But on the moon, we can set the baseline. So if we set the baseline, look at that picture. Isn't that cool? That's a real picture. Can you imagine those guys? Amazing. Anyway, so you calculate GPE at any height. You set y equals 0, whatever you want it to be, and then you calculate mgy, negative mgy, and g in this case would be negative 1.62. So you got to have the minus sign in there. And then if you know the kinetic energy at any height, like if you know that you're starting at 0 at height equals, 2.2 meters or something, you're dropping something, then you know the kinetic energy there. You're holding on to it, kinetic energy is 0. But, if you know the kinetic energy at any other point, that allows you to figure out everything. So if you know it at the top of the motion, at the bottom of the motion, or any intermediate height, then you can calculate total energy E. All right? So if you know the height, you can get GPE. If you know the kinetic energy at some height, you can get total mechanical energy. And then you got ditto marks all the way down the table. All right? And because you have ditto marks all the way down the table, the E column, you can figure out GPE and then kinetic energy, and actually the drop speed, V, which you get from V squared, the intermediate calculation is V squared, and then the drop speed is just the square root of that. You can figure that out at any, and once you get the E column, ding, you can get anything you want. A little bit of work. And that's what that talking PDF is about. All right, and that's what you guys are going to do here in just a second. You're going to calculate an energy for this guy dropping a hammer at a specific or from a specific height down to the ground, down to the surface of the moon. All right. So number 4 is my instruction to you that once you have the ditto marks column in the total energy column, you get everything else you want. And that's the power of conservation of energy. All right, let's go. Let's get this done. Hit the refresh key again. We're going to do a calculation. Okay. And here we go. Now this one's going to take a few minutes, so work with your neighbor. Astronaut drops the hammer from the small platform on the lunar module from a height of 2.2 meters above the surface of the moon down to the ground. What is its kinetic energy halfway down? At height 1.1 meters. All right, type in the numeric part of your answer to the nearest 0.001 joule, so to the nearest thousandth of a joule. All right, so keep a bunch of your digits and calculate carefully. All right, and this problem is like filling out 2 lines of the drop energy table for this hammer. All right. You know, so you have the top level, 2.2 meters, y equals 2.2. Figure out everything on that row. And then you can figure out the y equals 0. That's an easy. Once you get the top row, 2.2 meters, then 0.0 meters is a walk in the park. And then actually halfway is actually a walk in the park as well. So round off carefully. I see the first person to answer here. You just gave me about 7,000 digits. I don't want all those digits. I want something point something 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 out to the thousandth place. No. I want something point something something. No slacking. All right. Now remember, this is numeric, so you have to type in your numbers and then hit the send key. And I'll give you a few minutes to do this. And actually, if you have your computer, your laptop with you, you can look at that talk. You can't play it, of course, unless you have earphones. But you can look at it and see my straight. You see all my calculations for one of the rows in the talking PDF. 2.21 gigawatts. Three decimal points. Not 2. And not 7. Good. I see you guys coordinating and consulting with each other. Lauren, did you see your PDF? Good. Good. Kinetic energy is never negative. I see somebody with a negative number. NO. Kinetic energy is always, V might be negative, but kinetic energy is V squared, so negative times negative is always positive. So everything in the kinetic energy calculation is positive. Okay, good. I see you changed that. Nobody is getting it right. I got a lot of stuff, huh? Yeah, come on up. I can see a lot of people in the right ballpark, but they're not rounding off correctly. Yeah, Connor.
All right.
GPE, not GEP.
Yeah. So I got figured out at 2.2 and 1.1.
Yeah, so let me
I don't know
just
where to
double
go
check this. Okay, so this one's
That'll be the-
0.703,
Yep.
and there's the G,
Yep.
and 2.2. Okay, so that's the GPE at the top.
2.2.
Now,
Yes.
right, at 2.2. All right, now what's the kinetic energy up there?
0.
Right, so the total energy is this plus 0, okay?
You can use the
And,
total energy
yep,
equation.
and then, all right.
Big
And this looks good. This looks like a good GPE at 1.1.
1.
And you'll see a pattern when you do the...
It was like it just, you figure out half of it, then you get the rest.
yeah, halfway point is it... Hi,
Hi,
what's your name again?
Sierra.
Okay, Sierra. It's good, it's good. What do you
So,
got here?
I have a, okay, so this is what I got, but I'm
Sierra.
trying- yeah, I'm trying to, that's it? Yeah, I did it right?
Ding.
Okay, thanks.
Genius time.
Good question.
Yeah, you got it.
How do I enter it? I'm sorry.
Oh,
I'm not
boy.
good. I'm
Yeah.
not good with clickers.
Let me get my specs. Oh, you know what? You're on the you're on the YouTube.
I am.
Yeah, you're getting recorded here. All right, so you just gotta
That's okay.
see. No, it's good. All right, so you got.
Mm-hmm.
Then you go to the right, and then you go. I don't know. There's a decimal point. Okay, I think that's the decimal point. Okay.
Nobody got it yet.
Yeah, nobody's. See, look at this.
That's okay. I just,
Yeah, now you gotta. Okay, so to get to the next digit, you always go right, and
okay.
you gotta go up and
Oh.
choose, and
Thank you.
all right, and then you hit the send key when you're done.
So I found the easier way to do it because I went on YouTube last night.
Yeah.
Yeah. I'll tell you later. So
Okay,
for this, I just use that.
dude, that's. What do you think we're doing? That's the same. It's just a
No.
different symbol.
No.
You're
that's
using
the-
H instead of Y.
I know, but
See?
it looks confusing when you do it. But like,
Dude, you're burning my grits over here. No, it's the same. It's the same formula.
all right. Well,
Anyways, that's good. I'm glad. You know, sometimes what really helped you on YouTube is hearing somebody else explain the same formula. Because sometimes hearing it from two different directions by two different. That's why I say studying with a friend or somebody, or with me, another human, really helps. So even if the other human's at the other end of YouTube.
I'll see you on Wednesday because I started
Definitely.
looking over the talking PDF, but
Yeah.
help her out.
Yeah, good. All right. Thank you, Sarah. Good question.
Me and Jordan were talking about stuff, and kinetic energy transfer. We're trying to find the GPE, correct?
Hold on. Speak a little more slowly.
I'm sorry. We're trying to find this, correct?
No, you're trying to find kinetic energy. So, but if you figure this out, then now what's this?
That's when there was 2.2 meters.
Okay. So what's the kinetic energy at 2.2 meters?
But we don't have a velocity. Do we?
The astronaut drops the hammer. So that means he's holding it at 2.2 meters. So that means kinetic energy is 0 up there. So you can figure out at 2.2 the total mechanical energy, E.
Kinetic energy is going to be.
Yeah, see, this is good. Yeah, that's basically going to be the same as the total mechanical.
Adding zero, so
Now you're down at the next line, and now you start doing takeaways and stuff.
got it. So you're just plugging it in and then
Yeah.
subtracting because you're trying to find kinetic.
Yeah. All right. Good. All right. I see most of you guys have answers. Let me see. I don't want 7 digits of decimal. I don't want. I see a bunch of you with a good answer here, but you're not rounding off correctly. Get on the. 'Cause unfortunately, I don't see anybody. Sierra, did you type yours in yet?
Yeah.
Did you hit the send key? All right, let me see.
You see it?
No, not yet. This is weird.
You see it now?
No. Yeah.
Am I doing this correct? 'Cause are you just supposed to?
What is your name again?
Adriana.
Adriana, that's
I'm
right.
kinda
Okay.
confused. It is
Yeah.
how you do it. Sorry, it's a little my eraser's not.
Yeah, that's good. So that's the GPE at the halfway
Yeah.
height. Now, did you figure out GPE at the top? 2.2.
Why would I?
The reason that you would figure out GPE at the top is so you have the total energy.
Okay, but since
'Cause-
it's halfway, isn't GPE and kinetic energy the same? Because that's what it says.
So yeah, that's correct. So this is going to be the same as the kinetic.
Okay.
Okay.
So that's,
So you're good. Just get that number in there.
okay.
Hustle.
Thank you.
Am I on the right train of thought thinking that GPE is equal to KE in this situation? Because it's halfway down, so.
What? Yeah, that's not a bad idea.
But am I
Yeah,
being-
yeah, no, that's good. That's righteous. Halfway is a nice point to ask questions because it's. Yeah, I mean, if you get E to capital E anywhere, then the halfway elevation is sweet. It's easy. So, Sierra, you did it though, right? I have a feeling that this thing is not sending data.
I feel like it's there because it has like a check mark and it says like 4 times.
Actually, Sierra, could you come up here and let me bring your clicker? Let's just see. I want to. I'm gonna type in an answer here and send it, and it's gonna be a wrong answer.
That's okay.
See, now look at this. See, I don't have any. Nobody's got that, but what we've got is a ton of these people.
I don't know because
So-
she has the same answer as
See,
you.
look at that. It should be. I think this is coming through as that. So what I'm going to do is. Okay, I'm going to put this way up here,
That's okay.
and then I'm going to send it. All right, now that should come through. Okay, I got a check mark. I don't see it. See, that's it right there.
So did it like round it or something?
No, it's a number that. All right, I'm gonna have to mark this one correct. Let's put yours. Now let's see if we can. Oops.
Because I put DD for the frequency, so it should.
Yeah, no, we're getting you. Let's get back up there. Let's see if we can go to 57. Yeah. All right. I was okay. Thanks. Nobody was. What that shows me is that nobody's entering 7 digits. Okay. Thanks, Sierra. All you guys that I was yelling at about entering 3 digits, it's coming through as you're typing, and what I just did with Sierra, she typed in the correct answer, but then it came through with 7 digits. So this is really weird. Okay, let me close this. Anybody else still have an answer to put in? Okay, let me close the session, or close the question. let me show you. I'll show you what I got here. It's a little bit unusual. Come on, baby. All right. Now, here are the answers, and we sometimes look at the answers. Now, the correct answer is 1.253. And raise your hand if you typed in 1.253. Okay, very nice. Now, here are some bad ones. 1.25 rounded off incorrectly. 1.252 rounded off incorrectly. Now look at this. 1.253 should be between 1.252 and 1.254, but it came through as 1.2529999. Now that sometimes, if you ever do any computer programming, you know that sometimes the computer, see here's another one, 1.2549999. Sometimes computers they represent, see, look at this. I have no idea what this is. If I'm going to have to look at this, students. We shouldn't have anything like that. Looks like a malfunctioning clicker is what it is. Anyway, so this is the problem is with computers, they use a base 2 numbering system. So they represent every number as a set of ones and zeros, and it's perfectly fine. That's digital computing, but we use a decimal system, all right? And some decimal numbers in the binary system, lead to, this kind of blooped up answer here. It can't decide. So it writes in 1.25299. So we're just going to have to ride with that for now. Anyways, let's go back to the laptop. Here's your answer. 1.253 joules at 1.1 meter. And you can hear me talking to students up here. The halfway point is nice because if you figure out the energy at the top, the total energy at the top or anywhere else, that halfway point is 50-50. It's half potential and half kinetic. And that's because the energy decreases meter by meter. And it increments meter by meter, not second by second. Energy meter by meter. Now, I'm going to give you the downward speed. Go ahead and write this down. 1.89 meters per second at 1.1 meters. And you can verify that later as an exercise. Now, we're going to go through the calculation for that right now. So here's the calculation. It's no great shakes. GP equals minus mgy. And notice that I have all my digits. And I suggest that you carry digits till the very end. And you can see where I rounded off at the very end. So 1.113886 newtons for the weight force on the moon. And then 1.1 meters. So if you figure out GPE there and you know that it's halfway, then kinetic energies, and a bunch of you guys mentioned that, that it's before I mentioned it just now. If you figure out GPE at halfway, whatever that is, the kinetic energy is going to be the same. If you drop it from rest, if kinetic energy is 0 at the top, which, in this one it is, all right? And so the GPE is 1.252746, rounded off to 1.253 joules. All right. Now, let me just re-emphasize. You can verify the hammer's downward speed, which I mentioned just a few minutes ago, as an exercise. And, all you have to do there is download the talking PDF of the freefall tables that I mentioned earlier in lecture today, and work through that one, and then do something similar for the hammer on the moon. And you'll see the V is, what I said it was. All right, if you do that carefully. Okay, questions about the hammer on the moon? Yes. That's mg. That's the weight force on the moon. So 0.703 times 1.602 negative. No, excuse me, negative 1.62. Okay? And negative 1.62 is the value of G on the surface of the moon. Here on Earth, it's negative 9.8. From the top of Mount Everest down to the bottom of the Mariana Trench, the deepest point of the Pacific Ocean. But the moon's a different planet, and it's weaker up there at the surface. And, measurements, it's, negative 1.62. So the weight force, so mgy for the potential energy, completely different up on the moon. So if you go 1.1 meters above the surface of the Earth, completely different GPE. Because the Earth is a bigger planet. We have stronger gravity.
It's negative 1.62, right? So what did you minus or add to it?
The minus is this one right here. Let me get my cursor. So it's minus times 0.703 times minus 1.62, right? I looked it up on the internet. It's just for the hammer. That was like four or five slides ago. You were supposed to write it down, but anyways, that's the mass of the hammer that we're talking about. So yeah. All right. So 0.703, that's the mass of the hammer. All right. Another question. And I have a really, if you've looked at the calculations EPUB that I put up on web courses, you'll see the Tweety Turbo Jam problem in the appendix. That's like a total brain burner. It's based on a drop. It's basically doing a pretty fancy drop energy, freefall energy table on another planet, just like this one's on the moon. All right, now I want to start talking about chapter 5, chapter 5, angular momentum. Here's the front page of it. The object that is behind itself. Isn't that weird? That's a weird concept. The object that's behind itself. But if you think about it, it makes sense. If you have a circular object like a circular top or any kind of a cylinder that's spinning about the central axis of the cylinder, it's got a lot of kinetic energy because it's got a lot of grams that are in motion. So there's a lot of 1 FmV squared. There's a lot of P equals mv. But the direction of the V is changing at all times. The V squared might not be, but the direction of V is changing because it's in circular motion. And what Aristotle would have said is there's got to be something behind it or in front of it that's either pushing it from behind or pulling it from in front. That's how he explained the motion of an arrow. That the air rushes behind the arrow as the arrow goes forward and then pushes the arrow a little bit further, and then it, more air, and then pushes the arrow further and more, and that's how he explained the motion of an arrow, something pushing it from behind, the air pressure. And it was wrong. There was no way to figure out that it was right or wrong in those days, but we now know that's wrong. And the exception to his logic is, how do you explain something like a top or any other cylinder, a millstone? If it's circular, if it's spinning on its axis like a top, there's no way to get anything behind it because it's circular. So you can't, the only thing behind it is itself, the object that's behind itself. That's what Aristotle couldn't handle. So we're going to try to talk about that. Now, we're going to review a few questions about centripetal acceleration. We're going to go a little deeper into it. And the reason that we're going to do that is so that we can walk our way up into this profound and deep concept called angular momentum. And angular momentum is mysterious in some ways. We have here's a way to think about it that reveals its profundity, its mystery. Right now, we have the Big Bang theory of the origin of the universe. I know a lot about it. That's my research area. The Big Bang theory models all the galaxies of the universe as grains of dust, as if they were grains of dust, every galaxy. And so they have certain pressure and temperature expressions, energy expressions, momentum, curvature, everything like that. And the initial condition of all the galaxies was that it was initially, so it's not like you're at the top of the library and your initial condition is zero kinetic energy before you drop it. For the universe itself, the initial condition was this big explosion. The reason that we know that, the Big Bang, the reason we know that is because we can see now all the galaxies are moving apart from each other. Every galaxy is moving apart from every other galaxy, except for the ones that are really close to us. We have the Andromeda galaxy and a few other little galaxies near us. But other than that, every other galaxy that we see in the universe, and the further away that galaxy is, the faster it's moving away from us. So the entire universe is expanding, and that's the basis, the physical basis of the Big Bang theory. So we model the galaxies of the universe as grains of dust. In other words, if we were figuring out the curvature of a big whirlwind or a big mass of dust floating around, we would do the same thing as we do with the Big Bang theory. Now, here's the interesting thing about angular momentum. We don't consider the universe in the Big Bang theory modeling every galaxy as a grain of dust, a fluid of dust. We don't attribute any angular momentum to the universe as a whole. So we don't think of the universe as spinning. But if we did add that to the model, not only an explosion, but spinning, the universe itself, you're not listening. The universe itself would be a gigantic time machine. Think about that. In which you would always walk forward into your own past. And that's something called a closed time-like curve. But we don't think the universe has a spin like that. And but if you do have a universe made of dust and it's spinning, yeah, one big giant time machine. So angular momentum is kind of a cool thing to think about. And here's something that's very basic to think about. Racetracks. And I know that you guys, when you're out on the road, you're all responsible drivers. You never disobey the speed laws. You never go too fast around a corner, but some people do. And so let's Here's an iClicker. Let's do this. Hit your refresh key. Sorry, I didn't put in the refresh key on this. This is multiple choice. Driver X takes the track steady 88 miles per hour all the way through turn 1 and turn 2. Okay, so he's blazing through there. Which turn requires greater centripetal acceleration? Turn 1, turn 2, they each require the same, or D, it's not possible to determine. So there's turn 1 and turn 2, and there's driver X. I hear people clicking back in their notebooks to their notes about centripetal acceleration. I'll give you 30 seconds because you don't need to look at any formulas. Although if you do, it's nice. 20 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Oh my goodness. Well, it looks like we got a bunch of geniuses in here. Yeah, it's turn 2. That's most of you. And what? Okay. Go ahead and make a sketch of this for your notes because I'm going to give you the explanation in terms of this diagram. Now, he's going at a constant speed. So the thing that determines the amount of acceleration that he's got to achieve, with good tires and stuff and steering, is the radius of curvature at each turn. So over here, you can draw kind of an imaginary circle there for turn 2, and then you can do a little bit bigger one down here at this part of turn 1, and you can see that the two circles are bigger. All right? You would say, well, I've got a big turning radius. So that means that, a big turning radius, you're going to have some gription from your tires, but not a whole lot. But down there on turn 2, it's a lot tighter. So you're going to need some major grip, and that's going to produce some major centripetal acceleration. Okay, so that's question. That's the answer for this question. All right, here's another question. Scaredy Cat Joe. All right, so he's going through at 4 meters per second. I was looking for a picture of a kitty cat, so that one seems to be the nicest one. Even though he's looking a little scaredy. So, Scaredy Cat Joe, his centripetal acceleration compared to driver X at turn 1. So this is at the big turn. "30 seconds. "15 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Yeah, you guys are unjukable. Yeah, 80. Sounds like I did juke somebody over there on the right. Cut you napping. Yeah, the reason. So here's here's the explanation. All right. Joe's V is smaller, so the numerator is smaller in V squared over R1. And V, and this one you actually do need the equation, V squared over R for centripetal acceleration. All right. And so So R1 is the numerator for both driver X going through turn 1 and Scaredy Cat Joe going through turn 1. They have the same denominator, different speeds. So Scaredy Cat Joe's lower speed, therefore his V squared is smaller, therefore his total quotient is smaller. Now, we went from its centripetal accelerations to talking about galaxies and satellites and planets and stuff like that. So let's keep going with that. That's the Andromeda Galaxy in looking at it in infrared. And let's talk about orbits. We reduced them to a slightly similar, simpler formula that used orbital speed V, central mass m, and orbital size r. Here's the equation that we, that's kind of, that's not a force equation, and it's not an energy equation. It's a v squared equation. But it's the simplest way to, reduce the various physical factors: orbital speed, orbital size r, and central mass, capital M. And then, of course, Newton's constant, capital G. Right? Now, one thing that's nice is that on a circular orbit, the speed is related to the radius and the orbital period. Right? The orbital period is capital T. So for the moon, it's, what is it, 240,000 miles approximately for R, and about 28 days for capital T. And so you convert that into the orbital speed. And I believe it's about 1,100 meters a second or 11 kilometers a second. I can't remember, but you could calculate it out. All right, so this equation, GM over R equals V squared, you can actually also use it to calculate a relation between the orbital size, R, and the orbital period, capital T. And that's what Kepler's third law is about, which we talked about last week. Now, examples that we talked about, low Earth orbit. You want to view the Russians or something, you specify R, and you compute V. So if your altitude is 180 miles, and I calculated this out, your altitude is 180, that means your R is about 6,700 kilometers. And that's what we will call a low Earth orbit. It's a little bit below the space shuttle, but definitely close enough to take a look at the Russians. Then you've got to get a rocket that gets it up to about 17,000 miles per hour. And that's about 18,000 miles an hour. That's about the orbital speed for stuff, like the Mercury capsule was up at about that same altitude. About 90 minutes for one. The space shuttle, the space station, the Hubble is a little bit higher than that. But most of our spacecraft, manned spacecraft, are up there in the 17,000, 18,000 miles per hour altitudes. Connor.
So the altitude is how high the object is, and the radius is the radius of the object it's going around?
No. The altitude is how far it is above the surface of the Earth.
Okay.
And radius R is how far it is from the spacecraft to the center of the Earth. Okay? So it's the radius of the orbit. All right? So measured from the center of the Earth. Now NASA, they're not going to say, well, the space shuttle is 6,739 kilometers above the center of the Earth. They're going to say how far it is above the surface of the Earth. How far is it above the Kennedy Space Center, et cetera, et cetera. Okay, so that's the only reason. But technically they use R in those situations. All right, now let's do another example. The Geosynchronous communication satellite. So this is one where we specify the orbital period. And that kind of locks in the orbital size. You know, how far above the center of the Earth you have to go. So if the capital T period is 24 hours, which for geosynchronous you have to have, you know, whether it's geostationary or if it's orbiting above the equator, it's geostationary. If it's tilted, you know, like the space shuttle's slightly tilted. It doesn't go over the equator perfectly. It's got a little bit of tilt. But if you're, you know, so if you're tilted over the equator, that's good. You can still use satellites that do that to some degree. You would just call them geosynchronous. So the orbital speed is 6,900 miles per hour approximately. And that tells you that you've got to be out at about 42,200 kilometers. Altitude 35,900. That's about 6.62 Earth radii from the center of the Earth. So that's way out there. And the spy satellite, low Earth orbit, it's really close. And I've got a scale drawing of it next. So let's do that. Here's a kind of a combo diagram. Low Earth orbit, LEO, they call it. It's graphed in there, that black dashed line right up next to the Earth. Yeah, that's where the space shuttle is. They're just barely budged off the surface of the Earth. You know, they're out there. And here's another kind of a spy satellite, high eccentricity orbit. And the reason that this is handy is out here, the spacecraft at the far part at apogee, out here, it's going really slow. So if you turn you're up here for a few hours going around the corner, and so you got a few hours staring down at whatever is down here on this part of the Earth. You know, so you make that apogee right above Russia at noon, and you can see, you know, what is in Vladimir Putin's back pocket if he's out on the street at noon. You know, and we got satellites that can do that. All right, so that's a high eccentricity orbit. And here's geosynchronous. So this is the scale. So here's the Earth at about 6.62 radii is geosynchronous. You know, whether it's geostationary or just, you know, a geosynchronous orbit. Now the dynamics are controlled by Newton's law of universal gravitation. So we want to think about, and so that's a force, so we want to think energy and momentum, and because it's in circular or elliptical motion, we also want to think about something called angular momentum, right? And that's the topic of chapter 5. Now, here's another image from very early. You know, unfortunately, the website doesn't have page numbers on it. Did you notice that? It doesn't have page numbers. But this is one of the images from the website about Galileo's daughter and son, or maybe his granddaughter and his grandson. And, you know, the concept of torque, that's another vocabulary term we're going to be talking about today and Tuesday. Where you apply a force, you know, so if you're trying to go through and you don't even think about it, but you use the idea of torque all the time. When you're going out the doors, you're heading out to the hallway, you're trying to escape, you put your, look at the hand plates. Look back at the door. Everybody, look at the door. Look at the door. Look at the door. Look at the door, yeah. See, you got those are as far away as practical from the hinge. Now, you could press over close to the hinge, but it's not going to open very good because you're not putting a lot of torque. The further away you are from the rotation axis, every Newton is going to be more efficient the further away you are. And it's the same thing on this teeter-totter. You know, so here's the little shrimpy kid out here with a small weight force. That's the daughter. That's the little sister. And here's the big brother. He's got a bigger weight force out here. And here's the pivot point on this seesaw. Now, she can balance him if she goes out here. Now, if they're at exactly the same distance left and right, like point R here, she can't balance him. She doesn't have enough weight because she's smaller. But if she's smaller, all she has to do is go a little bit further out, and she'll balance him. And in fact, she can overbalance him. Leave him, he can be the one that's stranded up in the air. Did that ever happen to you when you were a little kid at the playground? Your friends, you get on the teeter-totter, and a bunch of other people get on the other end, and they don't let you down. And you're up there, Bob, crying. I hope that never happened to you. It never happened to me, but I've seen little kids, do that. I tell you what, little kids can be cruel. Anyway, so that's torque. Now we're going to talk some more about torque. And that's just the first little tidbit. Now, let's talk about angular momentum. Angular momentum is a special kind of momentum associated with spinning or with any kind of circular motion. So, a spacecraft might not be spinning, but if it's on a circular orbit or an elliptical orbit, you can describe its angular momentum state. But I like to start the whole idea of angular momentum by thinking about ice skaters. And you've seen the ice skaters at the Olympics. They start spinning, and if they start spinning with their arms out, or like this young lady with her. Could you do that on skates? I mean, I can skate, but I can ice skate, but boy, I wouldn't want to try that. But she's got her legs and her arms. And her center of mass is right over the skate, all right? And so she's trying to slow down in that position. But as soon as she brings, and you've seen this at the Olympics and stuff, as soon as they bring their arms in like this, oh my goodness, they really start spinning fast. That's the ice skater effect, all right? Bicycle wheels, spinning on the axle. And on Thursday, today's Thursday. On Tuesday, I'll try to bring in a bicycle wheel, and we'll do some demonstrations of angular momentum with a bicycle wheel. And you'll see the angular momentum. And did you know what? Angular momentum can be transferred from one object to the other. It's kind of cool. Through Newton's third law. So every centimeter of the tire is like a pixel. So it's got a few grams of mass. It's got some speed in meters per second. That's normal. So it's got some momentum. And all of it is oriented to the axle. It's not going from here to Oviedo. You can get a bicycle spiel, you put it on a little stand and you get it spinning, and it's not going anywhere, but it's spinning. So it's got some 1/2 mv squared. It's got some momentum, but it's not got momentum from point A to point B. It's got momentum always repeating its position if it's in a circular motion. All right? Now, that momentum, and I'll show you how to encode that for simple orbital systems, that momentum is called the angular momentum. The angular momentum is the momentum of spinning. The momentum of any curved path past a given axis. So, for instance, if we think about the angular momentum state of the Earth around the sun, or the angular momentum state of the moon spinning on its axis, or the angular momentum state of a comet orbiting the sun. But even if we have something going straight past the sun, it's not on orbit, it comes in close to the sun and then kind of veers off to a slightly different direction, we can compute, even so it's on a path near the sun, and if you make the sun your your focus, the origin of your axis, or the location of your axis, then you can calculate an angular momentum, even if something's not, even if it's on a straight path going past the sun. And, you know, we can do that. We can make something go on a straight path past the sun. It's not easy. You got to have good rockets and stuff, but you can do it. And stars go straight past. Stars are far enough away that they'll go straight past the sun. And we could compute the angular momentum of stars. The reason that ice skaters speed up is conservation of angular momentum. And it works a little differently. And we'll be demonstrating that on Tuesday next week. Now, I'm going to stop here and dismiss you. Your homework this weekend is one thing. Start reading chapter 5. Okay? You're dismissed.